the probability we saw before basically cared about a random experiment, right? What is a random experiment? How can we define a random experiment?
And which has equal probability of all its outcomes. It is
Mhm.
not biased.
Okay. Okay, good. So that's good. So these are the few things which we have to kind of streamline. Random means for us and for you in future, random means the outcome in some sense is not fixed. Every outcome has a certain there is a set of outcomes, and every outcome has a certain probability. You would like to say that if it is random, that means every outcome has equal probability. That's not what how we say it in mathematics. In mathematics, we will say it is uniformly random if everything has equal probability. But anyway, these terms we will encounter very often in this course. For now, random experiment is something where, you know, we believe that there can be many different outcomes. And actually, in real life, every experiment is random. If you have taken course, you must have taken labs in physics and chemistry. They say that, right? If you take the light, go through this prism or something, this kind of a pattern will emerge. And it is supposed to be a deterministic experiment, but it never turns out like that, right? The pattern will be different sometimes, pattern will be different that time. You mix two chemicals, sometimes you will get NaCl, sometimes it will explode. So essentially, almost everything in life is random, and that's why we need probability. But for us, since we need to define it more rigorously, we will remember a random experiment is something which have different possible distinct outcomes. And you have seen many such experiments and you have calculated probabilities for such experiments before. It could simply be tossing a coin. What are the possible outcomes in this case?
Head and tail.
Good. This is simple, right? You believe that it will not be, standing on the table or something. So there are two possible outcomes: rolling a dice, 1, 2, 3, 4, 5, 6. And yes, in many cases, it will be told to you that, all 6 faces are supposed to come equally likely. The probability of head is half, probability of tail is half. But this is an assumption which we make. And going further, it might happen that someone gives an experiment where these things are not. Someone can give you a biased coin and say, with probability 0.75, you will get head. With probability 0.25, you can get tail, or vice versa. These kind of things can happen. And then just for the most general case, which we will not care about that much today, something where there are infinitely many outcomes. And not just infinite, but even I would say uncountable outcomes, right? Pick a real number between 0 and 1. All these are random experiments. There are distinct possible outcomes. As most of you have seen, we would mostly assume that all these outcomes are equally likely. And once you have made this assumption, the probability of a certain event is captured by this formula. This was the lifeline for the probability case for us. Right? What is the probability of an event? Number of favorable outcomes, number of total outcomes. This is the most basic formula. This is very, very useful. But this is not sufficient for us. We are going to see how to change it, how to generalize it, right? That's what the objective for today's classes. But before we can make it a mathematical framework, the first observation is this course is for computer scientists and mathematicians. That means we are not really going to care about physical implementation of the experiment, right? Can we design a coin which has 0.75 heads probability, 0.25 tails probability? Can we create a dice which has 3 faces? All those are really not our concern. For us, an experiment or a random experiment will be described to us. I will tell you what does it mean. What does it mean to describe a random experiment? But once that random experiment is described to us, we don't care physically how that is achieved. Right? So what do we care about? If there is a random experiment, we want to figure out what are the list of possible outcomes. Is it head or tail? Is it 1, 2, 3, 4, 5, 6? Is it list of all real? It cannot be a list, but is it the interval of all real numbers between 0 and 1? What are the possible, I should say, distinct outcomes of your random experiment? And then we would also want from the creator of this experiment, what are the chances of these outcomes? Okay, they will tell us, oh, head comes with this probability, tails comes with this probability. If you are rolling a dice, phase 1 comes with, probability 1 by 5, 2 comes with probability 1 by 10, so on and so forth. But this has to be told to us. Both these should be specified for a random experiment. And once this is done, we will not worry about, oh, it was a dice, it was a coin toss, it was, how did we toss a coin? Did we flip it enough? Was it a coin from Amitabh, from Sholay? I don't know. Entire thing is specified. And we can make it very, very concrete. The probability, what we want as a description of the random experiment, we want 2 things. Most importantly, we want the sample space. It is denoted by omega in the literature most of the time, and we will also use the same symbol, sometimes different, but that will be specified. Generally, when people in probability write omega, that is the sample space. What is it? It is the set of all possible distinct outcomes for the experiment. Whenever you are given a question about probability, 99% of the time, the first thing which you should figure out is what is the sample space. Many a times it will be intuitively clear, that is fine. If not, you should make sure that you understand what is the sample space in these experiments, right? So when you roll a dice, what will be the sample space?
The integers 1 through 6.
Good. And I called it a set as opposed to what other things are possible?
A multi-set.
Yeah, a multi-set, or how you have taken a course in abstract algebra, a group or anything. We don't need any such structure. It's such a it's a simply a plain set. It's a splinest structure. It's a set. It's few elements. They have no order. They are just a list of, I shouldn't say list. List is order. This is just a set of elements. That's all I need to describe a sample space. And for today's class, let's worry about sample space, which is discrete and finite. Obviously, it need not be. For example, when we pick a random number between 0 and 1, it is not discrete. It is not finite. So we will worry about that, but later. Let's worry about the discrete and finite case for today, right? So if you remember the previous slide, we needed 2 things. We needed list of outcomes, which we modeled by a set. What other thing did we need?
Chances
Chances of each
Chances of, right? And the chances we will model by what we call a probability distribution function. Is this notation familiar to you? Is this something which I need to explain? Okay, then I assume if it is not clear, ask now, I can tell you. But simply put, this is a function where every element of omega is mapped to a real number. It's a function, right? So I'm assigning one real number to every omega. But it's not simply just any function. It has to satisfy two properties. The first property is that every value should be between 0 and 1. So effectively, I can say that my function is like that. Okay, this is another way to specify it. And if this is in saying that if you sum up probabilities, so this is probability of the outcome omega, if you sum up over all probabilities, it will sum up to 1. It is kind of capturing the fact that every outcome in omega is distinct, right? So that's why they are disjoint outcomes, distinct outcomes, so that their probabilities should sum up to 1. None of this is new for you. It's just the formulation, the way I am putting it. So whenever there is a random experiment, this is what we need to figure out. Either the person designing the experiment, the question will give it to us, or it will be specified through some assumptions. If someone says, oh, I'm tossing a coin and does not give any information, that means we will assume that the coin is, what do we assume? The coin is
Unbiased.
Unbiased. So the probability of head is half, the probability of tail is half. So
Rajat, there's a question in the chat.
yeah, can the probability for some outcome be 0? Because the definition is that every outcome must have some probability. Yes, it is not a problem. You can it just it messes up with you that there is an outcome. You can, those two kind of descriptions are same. You include it in omega and assign it a probability 0, or you just, it depends in what context you are working with. Any of the two formulations can be used. But yeah, at this point we allow p omega to be 0. Okay, this is a 0 and 1 are allowed. Okay, and this is slightly different because in most of the cases you saw before, the p omegas were all the same, right? If you had 10 outcomes, then p omega would be 1 by 10 for everything. We have generalized it. We have allowed every outcome to have a different. But now, as a beginner, I have a question. If everything is specified by the random experiment, the person who is designing the random experiment questions, they have given us all the probabilities. What are we supposed to do? In probability theory, what are we studying then?
Conditional probabilities.
Okay, that's good. But before that, there are other important things. Remember what kind of questions you were solving.
Sir, outcomes, like mixed outcomes, when they want a specific kind of outcome.
Yes. So a random experiment specifies omega and p for us. What we actually do in most of the cases is figure out the probabilities of events and work with the behavior like conditional probability and things like that. That is our job as a computer scientist or mathematician. Omega and p will be specified by the question or by assumptions. Once that is specified, we can figure out, mixed, as someone said intuitively, mixed outcomes, favorable outcomes, and things like that. And the mathematical way to define it is events. It is, what are events? Any subset of omega. To start with today's lecture, any subset of omega will be an event. And we would want to calculate probability of events. This is and different outcomes, and that's what you did in high school, right? So what should be, if suppose I have omega and I have a set W1, W2, W3, which is a subset of omega, what should be the probability of the event S?
1.
Sorry? No. It is a subset of omega, right?
Okay, sir.
So let's say you roll a dice, right? And omega is what will be omega for dice? 1, 2, 3, 4, 5, 6, right? And I say that I want the probability of having an odd number. That means my event S will have elements.
So W1, W2, and W3.
Probability
One,
of omega
one-
1
1,
plus
3, and 5.
1, 3, and 5, right? Omega 1, I don't know how I will map omega 1, omega 2 with 1, 3, and 5. Omega 1, omega just variables. But omega is 1, 2, 3, 4, 5, 6. We have a subset, let's say 1, 3, 5. This is what I'm interested in. What is the probability of getting 1, 3, 5, right?
Union of probability of getting each outcome omega 1, omega 2, omega 3. It would mean a probability of omega 1 plus omega 2 plus omega 3 minus the case where omega 1 and omega 2 are simultaneously probable for all three, and then adding ones.
Okay. So I see that there are still some confusions. Remember, omega 1, omega 2, omega 3 are distinct outcomes. It cannot happen that they occur together. Okay. So let me just take few examples and clarify this setting for you. We have events and we have sample space. For example, if you toss a coin, what is the sample space?
Heads or tails?
What if I toss a coin twice?
Heads, 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 tail, tail, heads, and tail, tail.
Good. So this is my sample space, right? And now what is my probability distribution function? In this case, if I say that the coin is unbiased,
Half like constant value.
what is the constant value?
1/4.
1/4. Right? So this is how I have defined the function. And now my event, let's say the event I'm interested in is number of heads equal to number of tails. Once I say that, my event S is fixed. What are the elements in S?
Tail, heads, and heads, tail.
Very good. And now the probability of S should be
1/4 plus
1/2.
right. So it should be probability of TH plus probability of HT. Again, remember, we assumed that these two were two distinct outcomes. So their intersection is not possible. This is okay. This is the mathematical frame. You can talk about rolling a dice. My omega, as you have already seen, is 4, 5, 6. Suppose I'm interested in the event that the face has a prime number. The top face has a prime number. What is my S then?
2, 3, 5.
5.
Okay. So this leads us to the debate whether one is neither prime nor composite, or is it prime and composite? What do people believe?
Neither nor.
Neither prime nor composite.
Okay.
Unique number.
Okay, so I will go with that. So this is set S, which is 2, 3, 5. And again, what is the probability of S? Probability of 2, probability of 3, probability of 5. Okay. And let's take a different case this time. Let's say this dice is funny. Probability of 1 is equal to 1/4. Probability of 2 is equal to 1/4. Probability of 3 is equal to 1/4. And now okay, again, you can't ask me how will I get this dice. That's something we don't care about. We are mathematicians. No offense to physicists, but we don't care about this. And now, given this now, what is this? What is probability of S now? What is the probability that I get a prime number?
1 6 plus 1 6 plus 1 6.
No, no,
Half.
it cannot be 1/6 now. Remember,
1 by 4 plus 1 by 4.
1 by 4 plus 1 by
Oh.
4
plus
plus 1 by 12.
plus 1. Right? So ask me questions now if this is not clear. Remember, this is what you did in high school. So all the probabilities were equal. But now I'm describing a different random experiment. The probability that the top face shows 1 is 1 by 4. Similarly for P2, P3, it's this weird dice where probability of 1, 2, and 3 is much more as compared to getting 4, 5, and 6. See, there's a question in the chat. Okay. Yeah, thanks. So any questions about this framework? Does it make sense now? These were the main distinctions. All the outcomes were distinct. The cases when you have intersection and union, we will get to it in few minutes. But to start with, every outcome was distinct and its probability was specified either by the question or by some. These probabilities need not be equal. And as soon as we do that, our famous fun formula of number of favorable outcomes by number of total outcomes goes down. We have to be here. Since all the outcomes were distinct, finding the probability of the set must be very easy. So now if I have omega, which is, let's say, omega 1 up to omega n, there are n possible distinct outcomes. If I pick 3 outcomes out of it, what should be the probability of S?
Probability of omega 1 plus probability of omega 2 plus probability of omega 3.
Omega 2 plus probability. Right? In general, probability of S is summation all omegas which are in S. And this formula is true because we have assumed that all our outcomes are distinct. We cannot. Remember, this is the basic, this is the start. Very, very soon, we are going to change into, we are going to talk about events, and then, 2 events can simultaneously occur and things like that. That's what we are going to do, but you have to wait for 5 minutes. To start with, this is the simplest thing, and this we did because we just didn't want to get stuck into cases when every outcome had equal probability. Now we want someone to specify what is the probability of each outcome, right? And once we do that, we can figure out the probability. Right? And this is just by summing up the. Any question about this? Let's take a few more examples. Suppose I have a bag where there is a red ball and a blue ball. I can't even see when I put my hand down whether it's a red ball and blue ball. I pick it up, I will get some ball. What is my sample space? Sorry, I should say omega.
Red and blue.
Red ball, blue ball.
Red and blue ball, right? What is my probability of red ball? What is my probability of blue ball?
1 by 2, both of them equally likely.
Yes. So we would like to say if nothing is given to us, we will assume that it is half and half. But now we have come to a college, right? So we have to take more general case also. It might happen that someone says, oh, the red ball is twice as big as the blue ball. And then these probabilities need not be, and we will take care of that. Okay, so it can happen that in your bag there are 2 red balls and 2 blue balls, right? There are 4 balls in total. The red ball is twice as big as blue ball, right? So then, okay, if you want to assume things, you will say that probability of picking a red ball is twice as much as picking a blue ball. Right, and then you can ask what is the probability of picking the red ball, right? So let me take that case. Omega so would be R1, R2, B1, B2. There are 4 balls, 2 red, 2 blue. What will be the probability of picking R1 and R2? They are both of the same size. They are twice as big as blue ball. So we assume that probability of R should be 2 times the probability of
1/3.
will be
1 by 3.
1 by 3. What about probability of B1, probability of B2?
1 by 6.
1 by 6.
1 by 6. Right? And then if someone asks, what is the probability of picking a red ball? That would be
2 by 3.
yes, that will be 1 by 3 plus 1 by 3 equal to 2. So these new things will happen. Right? So this is a red ball and blue ball. Let's take a second example. Amitabh tosses a coin twice. What is the probability that both the coin tosses give me head?
1 by 4.
1 by 4.
No. Again,
If it's a fair coin.
it's toss. Amitabh is tossing that coin, right? And I don't know
One.
whether a generation is familiar with Sholay. I would call it 1. Yeah. Thank you. Right. But in general, the question is not specifying it. If they are not specifying, then I would say that is unbiased. Probability is 1 by 4. Otherwise, they have to specify what is the probability of that, what is the probability of tail, and can be unbiased. Can be biased. Generally, when nothing is mentioned, we assume that things are unbiased. That's a safe assumption. So a slight distinction from what we saw before is clear. Now we have set of distinct outcomes which were there before. Previously, most of the time we would assume that all these outcomes were equally likely. Now there might be cases when we specify different probability. It doesn't matter. Still, we can figure out probability of the by this simple formula. Okay. So what are events? Can someone remind me?
Subset of the sample space.
Yes, and once you have subset of sample space, if you have subsets, you want to have fun with all the subsets. How do you have fun with sets?
You apply operations.
Yes, what kind of operations?
Intersection.
Okay, great. That is going to be our next job. But before that, I want you to answer this question. So you have this deck of cards and the numbers are written over it. 1 and 1000. 1, 2, 3 up to 1000. So there are 1000 cards and your cousin offers you this pack. She will pick a random number, a random card, uniformly randomly. So each card has equal probability of getting picked up, 1 by 1000. If the number comes out to be divisible by 2 or 5, she pays you 100. Otherwise, you pay her 200. Do you want to accept this fact?
Yes, sir.
I think you need a course in probability, otherwise you will lose a lot of money.
No, sir.
No, sir, we won't. No, sir, we won't.
Okay, so good. No, we won't. But why?
Because the expected amount that we win is coming out to be like negative, like you're losing.
Yes, that is correct. We will get to that formal expectation later. But how many numbers are there which are divisible by both either 2 or 5 or both?
Sir,
600.
Sorry,
sir,
600. Right, and that you can figure out easy. This is 500 plus 200 minus 100. And this is the exact thing which we will formalize very soon. So your probability of winning is 6 by 10. Her probability of winning is 4 by 10. So her probability is more than half of your probability of winning, but you are paying more, double of it. So intuitively, it should be clear to you that this is not a good trend. The amount of money should have been in the ratio of 4:6, but it is in the ratio of 3:6. The odds are bad. You don't want to. But don't worry, we will formalize it in future, as someone already said, we will calculate the expected return. It will come out. But intuitively, you should see that she will win. Her odds of winning are 4:6, but the payment she is doing is only 3:6. So this is a problem, right? 3:6 is same as 100:2. So intuitively, it should be clear to you that thoda to jhol hai isme, right? Something is a problem.
Sir, how is money 3:6?
Oh, because this is the money exchange, right? 100:200 is same as 3:6. Right? Like I've written this
Okay,
odds, but
okay.
100/200 is 1/2, 3/6 is 1.
This
And these are the odds of. Okay, but don't worry, we will find a formula and clarify clearly that if this happens, then. And this actually gives you a motivation to define expectation. But now let's go into detail. We said that we have these events as sets, so why don't we play with them? So now assume A and B are two events. That means they are subset of my sample space. They have their own probability, in terms of summing up all the omegas which are in A, all the omegas which are in B, so on and so forth. So now, what should be the probability of A complement? If
1
A is a
minus P.
subset, very good. Why? If A is an event, then A complement is also. It is also a subset of omega. And can you write a proof of this? Right? That's it's very simple. Probability of A complement is W element of A complement PW by our formula. This is equal to summation over all W minus summation over W element of A. Right? And now this is, what is this?
1.
1. And this is P of. So this is a small simple proof that probability of A complement is 1 minus 1. What about probability of A inter A union B?
probability of A plus B minus A intersection B.
Okay. Yes. So if A and B were disjoint, then the things were easy. Right? If A and B looked like this in the entire set omega, then I will just sum up the respective elements and then I would be done. But this is not going to be the case. Most of the time, my picture is going to look like this. And in that case, the correct formula, as we have already said, is P of A, P of B minus P of A intersection B. Can you formally prove it like I proved for PA complement? Just look at omegas. What are the omegas in A? What are the omegas in the combination? What are the omegas outside B? And you can easily. If this is not clear to you after the class, I can give you another formal proof of this. This is not clear. Okay, so the all of things which you learn for sets can readily be generalized for probabilities. So I learned De Morgan's law. Those were very, very helpful. Can you remind me what were De Morgan's laws for sets?
Probability of A
No,
union B.
let's not worry about probability at this point.
So A union B negation.
Yes, complement. So
Yeah.
is complement okay to you, right? Complement is same as negation.
Yes, sir. Is equal to like A's complement intersection with B's complement.
Very good. And A intersection B complement.
Is equal to A's complement union B's complement.
Right. So now, if I want to write probability of A union B complement, this will be equal to
Probability of A complement intersection probability. Well, intersection B complement.
Yes. And what will that be? From this formula?
Probability of A's complement plus probability of B's complement minus probability of A's complement union B's complement.
Very good. Right. So these are very, very simple things which you can do by yourself. All these set relations gives you relations about probability. And you can keep practicing it. There are few questions in the lecture notes also, which are on the website. You can just practice them. This is not hard. But my question is the framework clear? If the framework is clear, these kind of tricks are very simple. Okay. Again, you can. I will be happy to take more questions as after the class. If you just want to ask me personally, I would be happy to solve. Now, again, P of A union B union C. Our first estimate would be PA plus PB plus PC, but this is not going to be correct because we are going to count A intersection B twice. So then our second approximation minus, what should I write?
Pairwise intersections.
Yes. But even this has a problem. What is the problem?
A intersection B intersection C is removed twice.
Yes. So then, if I want to make it an equality, I should add B intersection. Right? And I get the exact form. Right? And if you were not sleeping in CS201, this should remind you of something we call
Principle of inclusion.
Inclusion,
exclusion.
very good. Yes. So this is inclusion. And just applying the same idea of inclusion and exclusion, we get this one. Okay. So if the notation is unfamiliar to you, I can explain the notation, but it's basically the previous formula written in a mathematical notation. Right? So we say that if it's a singleton single set, if we are taking the intersection of a single set like A, it should be positive. If even number of sets are getting intersected, then there should be a negation. And this is exactly what happens here. If cardinality of S, if the number of sets in the intersection are odd, then we get a +1. If the number of sets in the intersection are even, then we get a -1. So you should convince yourself that this is nothing but the formula for inclusion and exclusion. Okay. And now with that, what is the probability of union I element of n AI complement? Remember, how did we figure out the probability of AI complement? It was 1 minus
probability of AI.
Yes. And now, if you look at this, why I might be interested in this complement in many situations, we are interested in this union AI complement because we will think of AIs as some bad events. Okay, A1 is first bad event, A2 is second bad event, A3 is third bad event. We might have n bad events. And then, what is this probability?
Probability of good events.
probability of that no bad event. Right? None of the bad event is happening. Not A1, not A2, not A2. This is the general idea. This is why we are interested in this. And this is going to come out to be so just from the previous. And these are all easy exercises. Okay. So this one will correspond to S is equal to 5. This is something which bothers many people, but if I take the intersection of 0 sets, it should be omega and not 5. And this discussion we can have on it. But this is the mathematical convention. If you know, suppose S is equal to 5 and I take union of I element of S, here. What is this? If I take union over 0 sets, sorry, yeah, if I take union over 0 sets, what should this be?
0.
Yeah, 5, yeah. And if I take intersection of this should be the complete set. This is a notation, this is a convention we assume in mathematics, and there are good reasons for it. But yeah, let's skip this. Assuming this, then we get this formula for okay. Now knowing this formula, we can try this question. Okay, I will not go into the detail, but I will just ask you basic questions about the framework. Rest you can solve. And this is something which you must have seen in combinatorics course. Letters in an envelope. You have n letters numbered 1 to n, and you have corresponding n envelopes.
Rajat,
Yeah.
there's a request to explain the last part again.
Sure. Yes. So, so what I'm saying is that, you know, you all know what it means, A1 intersection A2. You know what it means, A1 intersection A2 intersection. Right? One way to write A1 intersection A2 intersection A3 is intersection over S. Sorry. Intersection over I element of S AI, where S is 1, 2. Right? Do you see this? Is this okay?
Yes, sir.
Right? And now I'm saying, what if S is equal to 5? It's an empty set. You should not call it a 0 set. It's my mistake. When S is an empty set, how should I define its intersection? You see there is a problem, right? It's not really clear. What should it be? Similarly, I can talk about this under the condition that S is.
My doubt is about the previous formulas.
Sorry,
No bad event happens. In that
sorry, go ahead once more.
the formula about no bad event happens.
Mhm.
In the second line, you wrote sigma s belongs a subset of n
Correct.
-1 power mod s, right?
Right, right.
I mean, how did the formula change to this? 1 minus that to this.
Because there was a minus sign, right? In probability
Yes.
union AI.
So 1.
So,
What about the 1?
yeah, exactly. So this is what I was talking about. So remember in the previous formula, the summation was when S was not equal to 5, right? So there is one more set in the bottom formula,
For s equal to 0.
or S is equal to empty set.
Empty
Let's
set.
not call it the 0. S is equal to empty set. And that is why I'm asking, what is this? And in mathematics, again,
Omega.
the discussion will be taken up in Hello if any of you want. But this intersection over AI is actually taken to be the complete universe. That's the convention. The union will be taken to, in some sense, for continuity purposes. And now, one, I can write it as probability of omega, or I can write as probability I element of phi. This is why this one.
Sir, student intersection also is a empty set.
Right? Some people might feel like that, but that is what I'm saying. It makes more sense to define it as the entire universe. And this is a standard mathematical convention. If you want to get the intuition behind it, argument behind it, we will discuss it on Hello. But remember, in mathematics, when you take the intersection over empty sets, it is actually equal to the entire universe. And this is in some sense for continuity. As you take sets of intersection of more and more sets, you are going towards phi. Right? So, but
Yes, sir.
but yeah, so it makes sense, and you think about it, we can convince. But let's not discuss it in the class. So it will take more time. But yeah, letters and envelopes. What is the probability that you have n letters and n envelopes? What is the probability that no letter goes incorrect? Again, you can see the calculation in the notes. But first, what is the sample space?
Some permutation of 1 through n.
Not some permutation, all permutations.
All permutations.
N factorial.
Yes,
Number.
exactly. This is n factorial. And now I want to define bad events. And what is the natural bad event AI?
Letter I goes in envelope I.
Letter I goes to n. And then what am I interested in? This in terms of AI. What is this? Probability of
Intersections of A.
not intersection, union, right? None of the bad events.
Union.
And then you can apply the previous formula. You can see what is the probability of A1 intersection, A2 intersection. That means letter 1, 2, and 3 are going to the correct position. I don't care about what happens to the other. All this you can calculate and get a formula for. But again, this is just calculations. You can see these are done in the notes. Okay. One more thing. Though I have given you the exact formula for this quantity, in most of the situations in computer science, actually the trivial bound is much more. So do you agree that probability of union over AI is less than equal to probability of A1 plus probability of A2 plus probability of AN?
Yes, sir.
Right, that's simple, right? Nothing to you can easily prove this. Because here there might be on the right hand side, some omegas might be repeated. Here, every omega on the left hand side is taken just once. This bound is very, very simple. You might think that inclusion exclusion principle applying the complete probability is more useful, but in most of the situations, this is the better. This is much more useful. And I can't prove it to you now. I have taken an example and again showed it in the notes. You can look at the notes, but such situations arise in computer science much more often. You will apply. This is called a union bound, or people also call it Boole's inequality. This will be used much more than inclusion exclusion. And people will just say union bound. You should understand what this means. It's the simplest thing. You should not get confused. Oh, what is this mean? Saying probability of union I element of an AI is less than probability of A1 plus probability of A2 plus probability of. I'm sorry, because of lack of time, I'm not going to detail. Probably in next class, I will cover this example. But this union bound is very, very
Since it's a bound, there should be a lower bound also, right?
this is yes, there are you might, in some situations you might need lower bounds, but in terms of usefulness, the upper bound of this is very, very useful, right? Because remember, intuitively, what were AIs? AIs were the
Right.
bad events, right?
Yeah.
And the union of AI was or probability of some bad event happening. So you want to say that, bad things will not happen with at least, at most this is the upper bound on bad events, and then we are.
Okay, sir.
So I'm not saying that you should not think of lower bound. What I'm saying is that in many of the practical applications, this upper bound turns out to be much more. And I'm giving you an intuition of my expertise. Okay, because these AIs are going to be bad events, and you want to bound the probability of upper bound the probability of any bad event. But we will lower bound is sometimes lower bounds are needed, and we will see how. What will be the trivial lower bound? Any lower
Zero.
bound? Too trivial. Can you come up with like a slightly better upper bound?
Summation P of AIs minus summation like pairwise.
Right, but then that makes things complicated, right? Because we have to calculate the probability of intersections. One of the trivial upper bound, lower bound.
A1 intersection, A2 intersection, A3.
This is a
intersection of-
better. No, A1 intersection, A2 intersection A, and you again have to calculate that problem. This is much simpler. No?
Yes, sir.
Right? So, but anyway, this is the talk of future. And I'm sorry for extending the class for 5 more minutes, but this time we saw that, what do we need to define a random experiment? What were the two things?
Set of
Outcomes
and
space.
chances of outcomes.
Yes, that means sample space and probability distribution function, omega and p, right? And then when you consider this omega and p, you can take the unions, intersections, which all are well defined and everything works fine if my sample space was discrete and finite. But things become interesting as soon as we go to the continuous case and need a slightly more general picture. That will be seen in the next class. That's all from my side. I would be happy to take questions. I hope I've answered all the questions on chat. Okay, please feel free to leave if you have no questions. Okay, I will see you on Friday. Bye.
Thank you, sir.
Thank you.